Today we're going to be talking about how to prove that three vectors are coplanar, and in this particular problem we've been given three vectors, the vectors u, v, and w. We need to prove that these three vectors are coplanar. Keep in mind or remember that coplanar means that all three of the vectors lie within the same plane. That's what we mean by coplanar. Well, how do we prove that these three vectors lie in the same plane? Well, the easiest way to prove this is going to be to find the scalar triple product of these three vectors. If we find that the scalar triple product of these three vectors is equal to 0, that's proof that the vectors are coplanar. Now, why is that true? It's true because the scalar triple product, whatever result we calculate for the scalar triple product, the scalar triple product basically gives us the volume of the parallelepiped figure defined by these three vectors. Well, what do we mean by that? If we have three vectors, and I'm not going to try to accurately draw u, v, and w, I'm just going to draw three random vectors here. But if I have three vectors, let's say that this is a vector called A, that this is a vector called B here, and that I have some third vector, C, these vectors are not coplanar. And if I fill in the other sort of sides of this figure, I end up with a three-dimensional figure called a parallelepiped, which is basically the three-dimensional version of a parallelogram, like this. So I have this three-dimensional figure here. I can kind of make it transparent and draw the back sides of it like this. But I have this three-dimensional figure. My scalar triple product is going to calculate the volume of this figure when I have these three vectors A, B, and C, which are adjacent and meet at this corner point right here. So it's going to calculate volume. Well, if I calculate volume and the volume is 0, then I know essentially that there's no height to my figure, right? That this vector A here, the height is 0, and I'm just left with a plane, which is, the base of this figure. If I only have a plane, if I have no volume, and I only have this plane, then I know that my vectors are coplanar and that the three vectors must lie in the same plane. So, A would be maybe something like this, where they all lie within the plane of the base of this figure. If my volume is 0, I know they must be coplanar. That's why calculating the scalar triple product is so convenient. So we want to calculate the scalar triple product and verify that it's 0. If we are able to verify that it's 0, we know that our vectors are coplanar. So what does the scalar triple product look like? Well, we'll abbreviate it STP for short. But when I calculate the scalar triple product of three vectors, here's what I'm going to do. I'm going to take the dot product of u and the result of the cross product of v and w. So I have something that looks like this, v times w like this. So notice here I'm taking the cross product of v and w. I'm going to get some result for that cross product, which will be a vector in the form A, B, C, like this. That'll be the result of my cross product. And then I'll have this vector and u. I can take the dot product of those two vectors. That's what gives me the scalar triple product, or the volume of this 3D parallelepiped figure. So given that, the first thing I want to do is transform my vectors u, v, and w into this form right here, where I just have the direction numbers of the component parts of each vector. I'm going to do that by taking the coefficients on I, j, and k. So the coefficient on I here is a positive 1, the coefficient on j is a positive 5, and the coefficient on k is a negative 2 when we include this negative sign here. So my vector u now is 1, 5, negative 2. My vector v, notice that I have no k term here, I just have I and j. Because I have no k term, I know that my z component here is going to be 0. So I'm going to get 3, negative 1, 0 when I take my coefficients. And then for w here, I'm going to get 5, 9, negative 4, like this. Now I have my three vectors and I can easily find my scalar triple product. Let's start with the cross product of v and w. We'll unpack this a little bit, get the cross product, then we'll put it back into the scalar triple product formula. So let's say here the cross product of v and w is going to be equal to, here's where we set up our matrix. We always put I, j, and k in our first row of our 3x3 matrix. Then we're going to take our vectors v and w and put them in our second and third rows respectively. So 5, 9, negative 4, we just take those direction numbers, we set up our matrix. Now we want to unpack this into its discriminant parts. What we're going to do Remember, when we unpack a 3x3 matrix like this, we're going to take I first in the upper left-hand corner. We're going to multiply that by this 2x2 matrix here, everything that's not in the same column and not in the same row as I. So here's what that looks like. We say -1, 9, 0, -4 times I. Now remember, we start with I as positive, we subtract J, and we add K. So we alternate with this pattern, plus, minus, plus. So we're going to subtract J's part here. Now for J, we're going to take the same thing, everything that's not in the same row and column as J, which is going to be this 3, 5 here, and the 0, -4 right here. So we put them in the same formation. We get 3, 5, 0, -4 multiplied by J. We just need to remember this negative sign. Then we're going to alternate. We're going to do a positive sign for K. And again, everything that's not in the same row and column as K, which is going to be 3, 5, -1, 9 times K. Now when we simplify this, remember that we're going to multiply the upper left and the lower right together. So -1 times -4 is a positive 4. Then we're going to subtract the product of the lower left and the upper right. 9 times 0 is 0, so we're going to get 4 minus 0 times I. Here we're going to get 3 times -4 is a -12, minus 5 times 0 is 0 times J. And then plus quantity, 3 times 9 is 27, minus 5 times -1 is a -5, multiplied by K. Now when we simplify, 4 minus 0 is 4, so we'll get 4I. -12 minus 0 is -12, so we have minus a -12, which will give us a plus 12J. 27 minus a -5 is 27 plus 5, which is 32, so plus 32K. So there's our cross product vector. This is the vector representing the cross product of V and W. We can also write it this way, 4, 12, 32, when we take our coefficients. Now we have this vector ABC that we talked about. We need to take the dot product of U, which we have right here, and this vector here, which is the result of our cross product. So taking our dot product, we can do that up here. We'll say the scalar triple product is equal to the dot product of U, so 1, 5, -2, like this, dot product 4, 12, 32, like so. Now remember that the dot product, to find the dot product, all we do is multiply the component parts of both vectors. So we're going to multiply our x components together, 1 and 4. So we'll get 1 times 4. Then we add to that the product of our y components, 5 and 12. And then add to that the product of our z components, -2 and 32. And when we simplify, you can see that we'll get 4 plus 60 minus 64. And if we simplify that, notice we get 64 minus 64, which is equal to 0. And that's perfect because remember, we were using the scalar triple product in the first place to verify that our vectors are coplanar. Remember that scalar triple product gives us the volume of this parallelepiped figure. Since we showed that the volume was equal to 0, we know that this parallelepiped three-dimensional figure here has no height. That means that all of our vectors must lie in the same plane. So we've used the scalar triple product to show that this figure has no volume, which proves that the vectors are coplanar.